Good afternoon, students. Even today, we are going to see about another experiment. So, hope last experiment was interesting. So, let's go into the slide. So, I have divided into two partitions. So, where first we'll see about how and what is that experiment, and then we'll see. We'll do it in real time, and then we'll see how that experiment works. So let me share the screen with you. Yeah, hope you're able to see, right? So in this laboratory electronic circuits 1 lab, today's experiment is going to be experiment number 3. So which is common collector amplifier using voltage divider bias. So this common collector amplifier is also called as emitter follower. We'll see why it is called as emitter follower and how or why it is a voltage divider bias. So why it is called as voltage divider bias. So we'll go from bottom up technique. So the agenda of doing this experiment is we need to design a common collector amplifier, especially using self bias or voltage divider bias. So then we are going to measure the gain, the bandwidth. We are going to plot it on a Semilog sheet, and we are going to find out what's the bandwidth. So that's the agenda. Let's move on. So firstly, we need to understand what is a voltage divider bias. For example, in yesterday's experiment, we saw fixed bias circuit. So why it is called as fixed bias? Because a fixed resistor was used to give bias. So biasing means it's a certain amount of voltage and current that is provided to the transistor in order to make it function. So there are active and passive devices. Transistor comes under active device. So you need to provide external voltage and current in order to make it function. So providing voltage and current depends upon various methods. So one of the method is fixed bias and another one is voltage divider bias, which we are going to see, right? So the term voltage divider, why it is called as voltage divider, so that's we are going to see, right? So this is a fusion word where it has two words, voltage and divider. So what do you understand from the word divider? So as you can see the pic here, so it's a room divider. It's used to partition rooms into two, right? So this you would have seen in practice. Similarly, what you see here right now is a road divider. It divides the road, or it partitions the road into two. So in one road you can go and another road you can come. So now if you see what is voltage divider, so it is going to divide the potential that is being given. So that's the idea, and that's why it is called as voltage divider. So hope in circuit analysis they would have taught you about voltage division rule. See, this Vin is the input voltage that is being divided using two resistors, and across one resistor you are taking a voltage. For example, if you have a 12 volt and you use an equal resistance of 1k and 1k, the 12 volt is going to divide it into 6 volt to 6 volt, right? So this 6 volt and some amount of current is going to be given to the transistor. Got it? So that's the idea. So here we are not using a single resistor to give bias. So if so, we'll call it as fixed bias. Here we are going to use two resistors to give a partitioned voltage or a divided voltage. That's why it is called as voltage divider. Or and the two resistors itself makes or takes care of providing enough voltage to the transistor. That's why it's called as self bias. So this is the circuit I explained in previous slide, right? So in our circuit, so this is how it will be. See, the two resistors are going to divide the voltage, and an appropriate voltage is going to go to the base of the transistor, right? So that's the idea. So let's go into the actual circuit. So our actual circuit here is common collector amplifier, right? So this is the circuit diagram. What you see here is a common collector amplifier. So how do I call it as a common collector amplifier? Because collector is common between input and output. So when you see suddenly, it seems like emitter is common. No, it is not common. So it is actually the collector that is common to output and the input through VCC. Or in other words, the circuit is called as emitter follower. We'll see why it is called as an emitter follower. Anyhow, in this construction, you have a voltage divider bias. Look on my arrow mark, means our cursor. You have two 150 ohms voltage divider circuit. So the 12 volt is being divided and goes to the base. The collector, it goes here, right? And there is an emitter resistance 10 kilo ohms. And you tend to take the output at the emitter. Or in short, to distinguish emitter follower or common collector and common emitter. In common emitter, the output will be taken across the collector and the emitter will be common between input and the output through ground. In common collector, the collector is common through VCC in between input and the output. Got it? So let's move on. See, the input is signal is given through a function generator. The specification of a function generator is 0 to 3 megahertz, and CRO specification is 0 to 30 megahertz. CRO, cathode ray oscilloscope, that's what we use. And other than this, there are two coupling capacitors to avoid DC offset. One is to the amplifier and another one is from the amplifier. Other than that, there's a load resistor, 4.7 kilo ohms, right? Let's move on. How to do this experiment? What is the procedure? So hope you would be familiar right now. Let's see specifically for this experiment. So first thing is you need to give the connections as per the circuit diagram. So circuit diagram I have shown in the last slide, right? Then what we need to do is we need to set an input voltage. Especially here in this experiment, we are going to keep 2 voltage. In yesterday's experiment fixed bias, we kept 20 millivolt, whereas here we are going to keep 2 voltage. And we are not going to disturb once we are set. So all we are going to do is we are going to vary the input frequency of the input signal and we are going to change the output voltage. So the input voltage is constant. The output voltage is going to differ according to the input frequency, right? So that's why it is called as frequency response of common emitter amplifier. We are going to study about how this common emitter amplifier responds for different sets of frequency. So that's the agenda here. So we are going to vary the input frequency and we are going to see what's the output voltage. Indirectly, we are going to see what's the output gain, right? So we are going to tabulate the reading then. We'll be plotting it on a semi-log sheet like yesterday. Then we'll find a 3 GB bandwidth. So procedure is as similar to yesterday's procedure. Or for all the experiments, the frequency response characteristics, it's the same thing. You will vary the input frequency and you'll note down what's the output amplitude. So input amplitude is fixed. Output amplitude will differ or output voltage will differ according to the frequency. That's the idea. Got it? So this will be the model graph. See, like yesterday, the output voltage will not drastically change. For example, yesterday there was a drastic change between, means below the cutoff frequency, like lower cutoff frequency and higher cutoff frequency. Whereas for common collector amplifier, it is not going to be. Whatever is the input voltage, most of the cases, 99%, the output voltage will also be the same. That's the uniqueness of common collector amplifier. Though it is called as an amplifier, the voltage gain is unity, right? So whatever is the input voltage, you're going to get it at the output voltage. So this is the tabulation. So we'll vary the frequency and we'll note down the output voltage. The input voltage is fixed, so that's why we have given it a constant here. And we are going to calculate the gain. So that is also in dB decibels. So that's why there is a 20 log here. So the gain is, it's the ratio between the output and the input voltage. So anyhow, I'll show you the readings once we take it. Right. Now, let me finish up by saying it why it is called as emitter follower. You can see that the output is taken across emitter. And also on the other hand, I said that the output voltage will be almost equal to the input voltage. In other words, the output voltage will follow whatever is given at the base. The emitter voltage means the output voltage at emitter is going to follow the input voltage at the base. That's why we call it as emitter follower. So though this circuit, common collector amplifier, doesn't works well as an amplifier, it is always used for impedance matching. So that's the application of common collector amplifier. It's used for impedance matching. Why impedance matching? They teach you in theory about only when the impedance is matched between source and the load, the maximum power will be transferred. So that's the idea. So emitter follower is not going to have a bigger gain. It's going to follow the input voltage, right? If I say input, it's going to follow the input voltage. You'll not believe it. Let's go and check it out, right? So it's time to do and learn, right? So I'm going to do the experiment and show you how it's going to work. Let's go. And do this experiment, right? So here is my setup. So I have a function generator to generate the input signal. So as told yesterday, I've selected sine waveform. There are three possibilities. You can generate sine, triangular, and square waveform. I have selected sine waveform, right? So this is the RPS, regulated power supply. I've almost kept 12 volt. And this is the cathode ray oscilloscope, which is used to visualize the time period display, right? So here is our circuit. Let me explain how I have connected. So the positive terminal from the RPS is going to the breadboard, from where I've used one resistor. It goes to the base. You can see it to the base, right? And there is another 150 kilo ohms given to the ground. This is the ground, right? Other than this, there is an emitter resistance. You see, here is the emitter. Let me point out using a pen. So here is the emitter, from which there is a 10 kilo ohms emitter going to the ground. Got it? And here is the output output capacitor, coupling capacitor, and there's a load resistor, right? So the input is given through a coupling capacitor, which is 1 microfarad, and yeah, this is how it's going to be. So we'll try to tabulate the reading. So I'm going to vary the frequency using this knob. You can see it here, right? So the maximum frequency is 3 megahertz, as I've told you. And here is the CRO's display. You can see the output signal. So before going to taking the reading, let me show what is our input voltage. So this is the terminal that is used to that I've used to connect the CRO. So from function generator, it goes to the base. So I'm trying to keep this at the base. Now I'm getting a signal. So let's measure how much is the voltage of the signal. So how do we measure it? So number of vertical boxes, 1, 2 into volt per division, right? So 2 boxes into 1. So the input voltage is 2 volt, right? So now I'm not going to disturb this. So this is the amplitude knob. If you want to output amplitude, increase the input voltage, you need to use this knob and change it. Anyhow, I'm not going to change it. All we need to do is we need to increase the input frequency and see the output. See, now I'm trying to place the CRO probe into the output. So it is taken across emitter, capacitor. Got it? So I'm getting an output randomly for 1 kilohertz. So the output is the same, right? One box, two into 1 volt per division. It is almost 2. So here is where I've tabulated the readings for you. So it runs from 200 hertz to 2.5 megahertz. So right now we saw what is the output voltage for 1 kilohertz. It is 2 volt. For example, we'll go for another frequency and we'll check whether it's constant over the entire range. For example, let me keep 200 kilohertz, 200 or 20 kilohertz. I'm going to keep 20 kilohertz here. So I'm trying to increase 19.8. Okay, 20 kilohertz. So 19.85 is okay, near to 20 kilohertz. So what's the output frequency? I mean, so what's the output voltage? It's again 1 box to 2 box, 2 vertical divisions into 1 volt per division. So that is nothing but 2 volt. So that's exactly what we got. So the input voltage is 2 volt and the output is also exactly, you're getting around 2. And you can see at 2.5 megahertz and 2 megahertz, there's a slight decrease, not so much. Only 0.4 is getting decreased. So note down the readings for 200, 500, 1K, 2K, 5K, 10K, 20K, 50K, 100K, 200K, 500K. It is the same 2 voltage. And for 2 megahertz, it's 1.6 and 2.5 megahertz, it's 1.2 volt. So when you do it using a calculator, about 20 log of V naught by VIN, since V naught by VIN is 2 by 2, 20 log of 1 is 0. So you get 0 here. And whereas here, you keep 2 volt and you get only 1.6. So it's a negative gain. So you got minus 1.3 and 4.43. So that's it regarding this common emitter amplifier. Right? So, common collector amplifier. So common collector amplifier is a unity gain amplifier. So it is used for impedance matching. That's what we proved, because the output at the collector and the output at the emitter follows the voltage signals at the base. So when you try to plot it, all you'll get is a straight line. So you'll not get any different graph like the previous case. You will get a straight line. So that's all for today. Hope you guys understood. So tomorrow we'll see another experiment, maybe on the same methodology. Until then, it's bye from GSL.